Okay, so basic properties of metals. These are the physical properties of metals. Most of the metals are solids at room temperature. Mercury is a liquid metal, so mercury can be treated as an exception. That means they have a shining appearance. So we say that they have a luster. So the surface will have a shine. Then most of the metals are hard. But then there are certain soft metals also, like sodium, potassium. So the soft metals can be cut with a knife. Most of the metals are malleable. Now, what is the meaning of this malleable? Malleable means that the metals can be
Beaten into
beaten
thin sheets.
with a hammer, yeah, to form thin sheets. But then they will not break because if you start beating with a hammer, they should not break. So this property of malleability is useful for application purposes. Gold and silver are highly malleable. So they may ask examples of some metals which are very highly malleable. So remember, gold and silver are the top two malleable metals. Then another property of metals is ductility. That means if you want to draw a metal into thin wires, it is possible. So elongation, that means elongation of the wire. That is, it can be stretched. So most of the metals can be drawn into wires. That is why metals are used to make wires. The wires which are used to connect electrical circuits. Gold, silver, copper, and aluminum are highly ductile. Then metals are good conductors of heat and electricity. So if you start heating one end of a metal rod, after some time the other end of the metal rod will also be hot. This is because it has flown from one end to another end, which means that the metal has conducted heat from one end to the other end. Electricity can also be passed in a similar manner. Electricity will be passed. Most of the metals have high densities. Most of the metals have high melting and boiling points. So the metal which has the highest melting point is tungsten. They may ask you which metal has the highest melting point.
Tungsten.
Yes, so it is tungsten. And what is the symbol for tungsten? How do you represent tungsten? Yeah, it's W. Capital W is the symbol for tungsten.
Uh, where is it in the periodic table? Tungsten.
Hmm. So you tell me. For that, actually, you have to know the positions of some other metals also. Otherwise, it's not easy for you to figure out. Because if you know which elements are located on the left side of the periodic table and which elements are located on the right hand side of the periodic table, so that way I
So
can
it must
tell
be on
you.
the left-hand side, sir. But what is its atomic number? Tungsten.
Exactly, that's what I'm saying. That it will, if you have to know the exact position, then for that you have to, you should have knowledge of period and block. I mean, the group period and block. Then only you can figure out, right? So for that, first you should know S block, right? Then P block, D block, and so on. So if I tell you about metals in general, if I tell you, then most of the metals lie on the left hand side of the periodic table, and the non-metals lie on the right hand side of the periodic table. And also between this extreme left and extreme right, in between also we have metals, right? So if I ask
Sir,
you about, if I tell you about tungsten, particularly if you want to know about tungsten, then tungsten is located in the middle. So neither is it on the extreme left, nor is it on the extreme right.
sir, it is in the sixth group, right?
Yeah. You want to know the exact group and period?
Yes, sir. That's what I was asking.
Yeah. Okay. So that is what. Likewise, see, for that you have to have a knowledge of D block, because see, if you want to know that way, then let me show you this. Wait. Okay, now see, if I tell you about the position, these are called horizontal rows, right? So if I'm going from left to right, that means I'm moving along the horizontal row. So these are called what? What are these called?
So these are periods.
Okay, that is one thing. Fine. And what about these?
Groups.
So these are groups.
Okay. Okay. Now, if I start with the first group, group one of periodic table, name some elements which are present in group one.
Hydrogen, lithium,
Hydrogen.
potassium,
Okay, fine. Then next group is group two. So name some elements of group two.
beryllium, magnesium, calcium.
Okay, okay. So that is group two. Fine. Then after this group two, which group do we usually take into consideration? I mean, for 10th standard, which
Group
group have you studied after group two?
13.
Exactly. You directly go to the 13th group after second, correct? Third group to 12th group, we are not studying now. So third to 12th, this entire thing comprises of many other metals, out of which one is tungsten, which you wanted to know. So this third to 12th, actually we are not dealing with in this 10th standard. We are only dealing with group 1, group 2, and then group 13, group 14, group 15, group 16, group 17, and group 18. So there are many elements between group 2 and group 13, and these elements are located in group 3, group 4, group 5, group 6, so on till group 12. That is how it is.
Sir, so what is the status of that valence electrons in these cases?
So,
Because
yeah, exactly. So that will depend, because we have to know the electronic configuration for that, right? So it may be 3, it may be 4, so it will depend. So for that, you have to know the exact electronic configuration.
I meant to ask that, like in 13th group, they have three valence electrons. So is it so that in the third group they
Yeah,
also
so
have
let's come to that. Okay, fine. So now see, if I'm talking about the third group, okay, third group. The first element which is most commonly used in the third group is scandium. It is scandium. Sc. What is the atomic number of scandium? Z is what?
So it's 21.
Yeah, it is 20. Okay. It is 21. Now, if I write down the electronic configuration of this, it is this. Actually, when you write electronic configuration of an element which has an atomic number of more than 20, then we don't write it in terms of shells. We usually write it in terms of subshells. So this is how we have to write.
3s2, 3p6, 4s2, 3d10, 4p6.
Yeah, exactly. So till 4s2 it is 20, and then again you say 3d1. After 4s, 3d comes. Okay. Now you tell me, if I ask you about the number of valence electrons, how will you count from here? Okay, first of all, what is the meaning of valence electron?
The number of electrons present in the valence shell, the outermost shell.
Okay, correct. So which is the outermost shell in this case for scandium?
Third shell.
No, outermost. Outermost means the last shell.
It's a fourth shell. Sorry.
Exactly, it is a fourth shell. So first thing is that. So get that thing clear. It is the fourth shell. It is not the third shell. The outermost shell is the fourth shell. Now you tell me, how many electrons are there in the valence shell of scandium?
3.
By 3.
Okay.
Which is
Is
the
it not?
valence shell?
Is it not the case like 2, comma 8, comma 8? It's not like that.
Yeah, okay, that is okay. That is a secondary matter. But as of now, tell me which is the valence shell. That is the fourth shell, right?
Yes.
So
Yes, sir.
this is the valence shell which I'm putting in a rectangle. Now tell me, how many electrons are there in the fourth shell? How many electrons are there in the fourth shell?
2.
हाँ एग्जैक्टली एक ही तो है ना फोर्थ, बाकी तो 3 दिख रहा है, तो 3 वाले को मत लो बैलेंस में. Okay. When I'm asking you about the valence shell, you will focus only on the outermost shell. That is the fourth shell in this case. And then count how many electrons are there in the fourth shell. So as of now, there are 2 electrons in the valence shell. So there are 2 electrons in the fourth shell. And that is why the number of valence electrons is 2. So if I ask you how many valence electrons are there in scandium, what will you say?
Two valence electrons.
2, yeah, it's 2 only. It's 2.
Yeah, but
Exactly.
is there
2.
something that one of its shell would have 9 electrons or the first shell would have 3 electrons? Because the
Means
maximum capacity of each shell is, 2 and 8, right?
no, that is not the maximum capacity. Maximum capacity of any shell is not 8. Told that is told to you just to simplify the concept. The maximum capacity of any shell is given by 2n square.
Yes, sir.
If you find out the value of 2n square for the third shell, what is the value?
18.
Exactly. So 18 is the maximum capacity of the third shell. Right. So 18 is the maximum capacity for the third shell. Similarly, what is the maximum capacity for the fourth shell?
It's
32.
Hmm?
32.
Exactly.
32.
Yeah, so 4 squared is 16 and 16 into 2 is 32. So the maximum capacity of the fourth shell is 32. Now, if I want to represent the electronic configuration of scandium in terms of the familiar configuration which you know, that is 2, 8, that also I can do. So let's do that now.
It would be 2, 8, 8, 3.
So 2, this 2 corresponds to number of electrons in the first shell, which means I'm focusing only on this part. So I write 2, comma. Now I will write the number of electrons in second shell. So what should I write now?
Sir, on which side of the board are you writing? On the right?
Left, this portion.
Okay.
Okay. So 2 is the number of electrons in the first shell. How many electrons are there in the second shell?
8.
Correct. So how do you get 8? Because you said 2 here and 6 here. So 2 plus 6 is 8. So 8. Fine. Now how many electrons are there in the third shell in this
8.
case?
8.
No. It's 9, right? Because we have 3s2, we have 3p6, and we have 3d1 also.
Okay.
So 2 plus 6, 8 plus 1, 9. So 9 electrons are there in the third shell. Because I'm talking about the shell, I'm not talking about the subshell. The shell means it's 3. So wherever you see 3, you will have to take that into account. That means 3s, 3p, as well as 3d. And now I'll come to the fourth shell. How many electrons are there in the fourth shell?
2.
So this is the electronic configuration of scandium. 2, 8, 9, 2. So you can write it in this manner also. But in order to write it in this manner, first you have to write it in terms of subshells. And then you can convert that to this form, the way I did.
Is there any way to write it in subshells? Because I have.
Yeah, obviously there's a particular way to write. You will have to know the maximum capacity of each subshell. That's all. So the maximum capacity of S subshell is 2. The maximum capacity of P subshell is 6. The maximum capacity of D subshell is 10.
Okay.
Okay, that is how it is.
Okay, sir. Okay, sir.
So now if I want to talk about, let's say this one, Fe. Atomic number of Fe is how much? 26. Now again, let's try to write down the electronic configuration in terms of subshells. So I'll start with 1, 1s2, then 2s2, and then 2p6. Tell me, what should I write next? What I should write after this? After
So 3
2p6?
is 2. 3p6.
No, no. After 2p it is 3s.
So 3s2.
So
So
3s.
3p6.
Yeah, after 3s comes 3p.
So 4s2.
Okay. After 3p comes 4s, and maximum capacity is 2. So 4s.
4p6.
And after 4s again we have 3d, right?
3d.
Now how many electrons should you write in 3d? So
So 3d6.
look at the total number of electrons in Fe. 26 is the total number. So 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 6, 18 plus 2, 20. Already I have used 20 electrons. That means I'm left with 6 electrons.
6 valence. 6.
So 3d6. 3d6. Okay. Now convert this to the usual form that we are familiar with.
So 2, 8, comma.
So 2 is the number of electrons in the first shell, then 8 is the number of electrons in the second shell, and then
So 14.
okay, so let's count the number of electrons in the third shell. So 2, that is 3s2, so 2 plus 6, that is 3p6, so 2 plus 6, 8 plus 6 in 3d6, so 14. Then after 14, we have to look at the last shell, which is the fourth shell, which is 2. Again, it is 4s2. So this is the electronic configuration of Fe. Okay, is it clear now?
Yes, sir.
Right. Now, let's go ahead with the properties. That means for an element, first we are supposed to write down the configuration in terms of subshells, and then we can convert it to the shell format. Okay, these are the physical properties of metals. Now, non-metals. So, a non-metal has 4 or more than 4 valence electrons. And non-metals are less electropositive than the metals. Non-metals are less electropositive than the metals, which means that metals are always more electropositive than non-metals. Why so? Because in a metal, I have 1 valence electron, or I have 2 valence electrons, or I have 3 valence electrons. So it is easy for a metal to lose its valence electrons. Anything which loses its valence electrons becomes positively charged, and hence we call it electropositive. Whereas a non-metal has a tendency to accept electrons from outside. If it is accepting electrons, that means it will acquire negative charge. So we say that a non-metal is more electronegative than a metal. Right? That is how it is. So a metal is always going to be more electropositive than a non-metal. So indirectly, I can say like this: the electronegativity of a non-metal is higher as compared to the electronegativity of a metal. Physical properties will be opposite to those of metals. So non-metals are brittle, means they are not hard, they are brittle. They are not malleable, they are not ductile. They are poor conductors of heat and electricity. In this, you have to remember one exception: graphite is a good conductor. Graphite is a non-metal, but it is a good conductor. So they ask you often, name a non-metal which is a good conductor.
Graphite.
Yes. Non-metals are not sonorous, so you don't get noise or sound when you strike a non-metal with a hammer or some object. And also non-metals are non-lustrous. That is, they don't possess any glitter or shine on the surface. But again, you have to remember this exception. Iodine has a shine. Iodine is a non-metal, but it has a shine. So exceptions are very favorite things for examiners. Okay, now one thing somebody has asked about tungsten. Tungsten is the name that we use, that is fine. But the Latin name of tungsten is wolfram. Hence, the symbol is W. Just like sodium, you don't write S, right? For sodium, you write Na. This Na comes from the Latin name of sodium. Potassium. So K is the symbol for potassium. So K comes from the Latin name of potassium. Similarly, for tungsten, we write W. W stands for wolfram. Okay. So WOLFRAM. Check the spelling. Fine. Now, this is one important aspect. Non-metals may be solids, they may be liquids or gases at room temperature. So we cannot generalize that all non-metals are liquids or all non-metals are gases. We cannot generalize. Then I have two examples of
Sir, but there
non-metals.
is only one non-metal that is liquid, right?
Bromine, right?
Yes.
Hmm. But there are many solids, there are many gases.
But there is only one liquid, right?
Yes.
Okay.
Yeah, so these are gases, and iodine, phosphorus, sulfur, carbon, etc. These are solids.
So I have a doubt.
Hmm.
Sir, if bromine is liquid, so why do we I mean, mix it with water to do the bromine water test? Why can't we just do it like with
Means
the liquid bromine?
no. That is a different scenario altogether. There you need to add water because of the mechanism. For that, you have to understand the mechanism, which is beyond the scope at the moment. Because bromine and water will react and form some species, and then the attack happens on the substrate. Because if you want to carry out a test for any organic compound, then the reactivity must be enhanced. So we ensure that it reacts. That is the reason. Because you are performing the bromine water test for a compound which contains a double bond or a triple bond. Now, for that, in order to make this react, you need something called, there is something called electrophile. And in order to generate the electrophile, we use bromine water.
Okay, sir. Okay, sir.
So for that, you will have to know about nucleophile and electrophile. Then only you will be able to understand, which is done in 11th standard. Okay. So generally, non-metals are hard. I mean, they're not very hard. They are medium, or they could be soft. But then diamond is the hardest natural substance known. Diamond is a non-metal, so exception is always there. Usually non-metals are not very hard. Again, non-metals have low densities, but iodine has a high density.
And so iodine is lustrous also, right?
Yes. Now you have to know some names of metals. So I've given these names. These are the most commonly used metals in reactions and also as examples. So you have to know these. These are the symbols. Below these symbols, I have written the actual names of the metals. So you can have a look at the names. Look at the names. Spellings have to be clear. Don't make mistake in the spellings.
Will the scientific names be asked in the exam?
Yeah, they could be.
Okay, sir.
Similarly, we have Latin names for other metals and this thing elements. Like Sn is the symbol for tin. Pb is the symbol for lead. So you must be aware of the symbols and names of all the metals which I have written. So most of the names are familiar to you. Similarly, you should know some common nonmetals. Now comes a very important part. You must be thorough with the electronic configuration of some elements. So from 1 to 20, you have to be thorough with the electronic configuration. So these are the elements. Their atomic numbers are mentioned in the second column and their respective electronic configurations are mentioned. The first number is 2. That means there are 2 electrons in the first shell. Then you put a comma and you put the second number, and the second number stands for the number of electrons in the second shell. Okay, now if I ask you that what is the similarity between phosphorus and nitrogen?
They both have 5 electrons in their
Yeah. So
valence.
nitrogen has 5 valence electrons, as you can see here. Also, phosphorus has 5 valence electrons. Okay. So they will be chemically similar. In calcium, we are supposed to know the electronic configuration. Now let's understand some things which are based on the valence electrons. So this is the first thing. So lithium, sodium, potassium, rubidium, and cesium are called alkali metals. Every alkali metal has one valence electron. Similarly, beryllium, magnesium, calcium, strontium, barium are called alkaline earth metals. Every alkaline earth metal has two valence electrons.
So, in spite of hydrogen being in the first group, it is not referred to as
It
an
is
alkali
it
metal,
is
right?
not a metal, so we cannot call it
Okay.
an alkali metal.
Okay.
Hydrogen is a non-metal. Nitrogen, phosphorus are called nitrogens. Every nitrogen has five valence electrons. That means we are talking about group 15.
So why pygnogens?
That name is derived from a Greek word. That is why. Greek.
Okay, sir.
So group 15 elements are called nitrogens. Also, you can call them nitrogen family. Similarly, group 16 elements
Sir,
are called
can you
chalcogens.
move up to the point second?
Which one?
So point number 2. Okay, sir.
Okay, now this nitrogens are in group 15.
Sir, isn't there any specific name for these group 13 and 14?
No, we just say group 13 is boron family and group 14 is carbon family.
Okay, sir. So do we not call them organic compounds like? No. Okay.
No, we cannot call. The organic compounds are compounds which contain carbon as
Carbon.
well as hydrogen. And apart from carbon and hydrogen, there may be other elements as well.
Okay, sir.
So will the group such as functional group will not be termed as hom- hydrocarbons?
See, I'll tell you, if I have any compound which has only carbon and hydrogen, then only I will call it a hydrocarbon.
Hydrocarbon.
Apart from carbon and hydrogen, that is in addition to carbon and hydrogen, also if there are other things, then I cannot call it a hydrocarbon. Then I have to
No, sir,
call
I'm
it.
asking for functional group.
What is the question?
So my question is that the groups such as functional group carboxylic acid are also not termed as hydrocarbons, or they are termed to be.
No. They cannot be called hydrocarbons. Hydrocarbons are only those compounds which have carbon and hydrogen. That's it.
Okay, sir.
I cannot call a compound a hydrocarbon if it has carbon, hydrogen, and also something else. So oxygen is present, right, in some functional groups like carboxylic acid or aldehyde or ketone. I cannot call such a compound hydrocarbon because in a hydrocarbon, no other element except carbon and hydrogen is allowed. So oxygen is not allowed in a hydrocarbon. Similarly, nitrogen is not allowed, sulfur is not allowed in a hydrocarbon. Only carbon and hydrogen should be present in a hydrocarbon. So group 17 is this. Group 18 has the inert gases. These are the inert gases.
So is the group 18 also termed as zero group?
Yeah, zero group. Zero group. Correct.
So is it due to its zero valency?
Yes.
Okay, sir.
Any inert gas has a zero valency in most of the cases.
Sir, what is the exception?
Xenon. Xenon forms compounds.
Sir, so was xenon first discovered as a noble gas? As it
That I have
found.
to check. You mean to say that the first noble gas to be discovered?
Yes, sir, because it only showed reactivity. So
Then I have to check that. Which was the first inert gas to be discovered?
okay, sir.
Okay. Now,
So what type of bond does xenon make?
covalent bonds.
Okay. So doesn't it have okay.
Because electrons are shared. That is why.
Sir, so if the electrons are shared, then it would have more than 8 electrons in its valence shell.
See, for example, I'll show you. That's okay. That is not a problem. There are many compounds where the central atom has more than 8 electrons. Okay. So if I show you this one, here what is happening? This is the structure of HCF2. So how many electrons do you find around xenon now in total? 10 electrons.
Yes, sir.
How 10? This is having 2. This bond also means 2 electrons. This is 2, this is 2, this is 2. So 10. Correct?
Yes.
Yeah, so fine, that's fine.
Okay,
Xenon
sir.
has, because xenon has d orbitals also, so it can expand its octet.
Okay, sir.
If an
So, sir,
element
what
has
is
d orbitals, it can expand its octet, which means it can hold more than 8 electrons in a bond.
so what is that?
Hmm?
So what type
And
of
so
what
that
is that
doesn't that
characteristic?
change the property of atomic sizes in the periodic table?
Means size is defined for an isolated species, right? Size is
No, sir. Means in this year we have means in 10th we have said that sizes means we have found the trends among sizes. So can't this be a means can this prove our assumption wrong that about sizes?
The
what is the connection
sir,
of
the trends are
size?
sir, the trends are not applicable for the noble gases, I guess.
No, but what is the connection with size? Every if you're talking about the trend in size, then if I go down the group in 18th, that is if I go from helium till radon, the size is increasing only, right? Helium is the smallest one in size.
Yes, sir.
So what is the connection of size with the formation of bonds? Size has
No,
got
sir. Not
nothing to do with
formation of
formation of
bond. That
bonds.
having more than 8 electrons in the valence
How
shell.
does that have connection with its size? Size is with respect to the radius. कि उसका radius कितना है from the nucleus. That is called the size. And formation of bonds is connected to the capacity. That is the availability of orbitals.
Okay, sir.
Size has got nothing to do with the capacity.
Sir, so all its other shells has larger number of electrons than 10, right?
Which one?
Xenon.
Compounds in xenon.
Sir, not the compound. So the element xenon has more than 10 electrons in its other shell.
Yeah,
Except
other shells. Yes, yes. But
okay.
that is because any shell, as I said, the maximum capacity of any shell is given by this. So
Yes.
for the third shell, it will be 18. For the fourth shell, it will be 32. Helium is the only inert gas which has 2 valence electrons. All other inert gases have 8 valence electrons.
Sir, except xenon, right?
No, every inert gas has 8 valence electrons.
But sir, xenon has 10, right?
No, that is after formation of bond. वो तो
Acha.
compound पे depend करेगा ना.
Okay, sir. Okay, sir.
In which compound it's having how many valence electrons, that will be decided by the formation of the compound. I'm talking about only xenon, when xenon is alone as an atom. Atom means it has not yet formed any bond, it's alone. Okay, now chemical properties of metals. Reactions are asked in the exam. So these are the reactions. Some common reactions are supposed to be quoted as examples. First type of reaction is this. Okay. Metal reacts with a dilute acid to form salt and hydrogen gas. Examples: H2SO4 is an acid, Mg is a metal, so it is reacting. Mg is reacting with H2SO4 to form salt and hydrogen gas.
Displacement reaction.
Yeah, so this is a displacement reaction. Similarly, the second one, if you see, zinc is reacting with HCl and forming hydrogen gas. HCl is an acid. So a metal reacts with an acid to form salt and hydrogen gas. But all metals do not react with acids. So you have this note.
Aluminium and zinc.
No, copper, gold, silver, platinum. These do not react with dilute acids.
Okay, so sir, because they do not, they are not so reactive, so they need concentrated acids, or is there any?
Yes. So they are below hydrogen in the reactivity series.
Okay, so there's no other reason behind it, right?
It is related to electrochemistry where you check oxidation potential and reduction potential. So the actual reason is that. But in 10th standard, we just say that it is below hydrogen and so it is not reactive. But the actual reason is related to your electrochemistry, wherein we see which is having a higher reduction potential and which is having a lower reduction potential. Based on the values, we take a decision. So in the exam, if they ask you a reaction with copper, then you will say that there is no reaction happening if copper reacts with an acid. Same holds true for gold, silver, and platinum.
So if it's below hydrogen reactivity series, then how can it even react with concentrated?
Anybody has any doubt?
So can you hear me?
Yes,
So I was asking.
I cannot hear now.
Now can you hear me?
Yes,
I was asking whether it, how can
again, I cannot hear anything. You do one thing, you can write it and you can send it to me. Okay, now if I want to write one reaction, now see the problem is usually to understand the formation of salt, or rather to write the formula of the salt. That is the most common problem which people face. For that, what to do? So for that, we have to know a list of ions. And once we know those ions, we can easily write the formula of salt. Without the list of ions, you will not be able to write the formula of the salt. Now, some common ions you have to know. Unless you know the names of the common ions, you will not be able to write the formula of any salt. Because salts are very important. You will need salts in the chapter called acids, bases, and salts also. Unless you know how to make use of the ions, you will not be able to write the formula of the salt. Okay, keep this thing in mind. So what to do for that? We can learn a few commonly used ions, and those few commonly used ions will help you out whenever you need to write the formula. Okay, so some commonly used ions, if I have to show, very commonly used ones. So you have to know that list. So I'll show you that list. So I've got this one where you have to know the list of ions. First of all, we'll start with cations. Cations are positively charged ions. Cations are positively charged ions. So these are the common cations that you have to know. So I'll give you example of a salt, and these are the anions that you have to know. Okay. So unless you know these anions and cations, you will not be able to go ahead. So I'm giving one example now. Let's say I have to write the name of this, the formula of this salt. That is, let's say I have to write down this. Then how to write the formula of this salt? First, I will check the cation, and then I will check the anion. This is the cation because whatever is written before is the name of the cation. This is the anion. So that is the first thing. Identify the cation and the anion. Once you have identified, then see what is the charge on each ion. Calcium is this, and the charge on calcium is this. Why? Because calcium belongs to group 2 of periodic table. I will write in this manner. So this is my cation. Now I will write the anion. Let's look at the anion. So perchlorate, this perchlorate ClO4, and then you have -1 as a charge. So perchlorate is what? ClO4 and then -1 as a charge. So I will write here ClO4 and then -1 as a charge. First I'll write the cation and the anion. Now I can write the formula of the salt. How? This 2 will come here, this 1 will come here. So Ca, 1. This 1 comes down. And the 2 also goes to the other side. So I have to write 2 after ClO4 as a subscript. I must put brackets and then write 2. So this is going to be the formula of the salt. The salt is calcium perchlorate. This 2 comes outside the brackets and it comes below like a subscript. So please ensure that you write the formula of the salt in this manner. And you need not write this 1 below calcium. So you will just write in this manner. This is what you will write. This is calcium perchlorate. Okay. So unless you know the formula of the cation and the formula of the anion, you will not be able to go ahead. Let's try another salt. Let's say I want to write this. I want to write this. Potassium. Potassium. Sulfite. If I want to write potassium sulfite. And again, potassium is my cation and sulfite is the anion. So I will write here K plus 1. The charge in potassium is +1. So I will write +1 on top of K. Okay. And sulfite is the anion. Let's try to find out where sulfite is. Can you see this is sulfite? SO3 2 minus is sulfite. So I'll write that. So SO3 2 minus. This is sulfite. Now this 2 will come here. 1 will go here. Okay, 2 SO. This will be the formula of potassium sulfite. Okay. Any doubt?
Hello, Rushi Bhash बोलतोय. Hello.
Okay. So unless you know the names and the formulae, you will not be able to go ahead.
Hello, भावेश बोलतोय. अरे मी तुला एक PDF पाठवला.
So potassium sulfide is going to be this
Sir,
K2SO3.
I'm not able
व्हिडिओ
to.
पाठवतो. त्याच्यावर जे डिझाईन
Any
केलेलं आहे
doubt?
ना त्याच्या काय ना जरा आणि साहेबला पाठवतो. त्याला जरा सांगतो मी उद्या जायला.
Let's try another salt.
हा ते रिपोर्टच आहे तो त्याच्यात त्यांनी काही दिलेला असेल.
Another salt.
हो हो म्हणून
Let's say I want to try this.
ते लोकरीचा ग्रुप होता ना
Aluminium phosphate. Then what will happen?
Sir, is it AlPO4? Sir, is it AlPO4?
Yeah, correct. So 3 plus I will write here.
Sir, there is a lot of background sound coming. Sir, I'm not able to hear you.
Okay. So I don't know from where it is coming.
Sir, maybe some others mic may be on.
Okay. So then I okay. Fine. Now Al plus 3 is the formation, is the cation. And let's look at the anion now. This is the anion, PO4 3 minus. So 3 comes here, 3 goes there. Three and 3 get cancelled. And so I'm left with AlPO4. This is how I'm supposed to write the formula of any salt. Okay. Any doubt? Okay. So let's try to write down the formula of a salt which is produced after a reaction. So let's say I have this reaction. Aluminium reacting with HBrO4. Metal, this is a metal. This is an acid. So metal plus acid will give me salt plus hydrogen. For the salt, again I have to make use of the cation and the anion. So Al3 plus and the anion is BrO4 minus. So 1 comes here, 3 goes there. So what will happen? AlBrO4. This is the formula of the salt. Okay. I have to balance the reaction. I'll put 2 here, 2 here, 6 here, and 3. Now it's balanced. This is how you have to write the formula of salt, and this is how you can write any reaction taking place between an acid and a metal. Let's try one more. So salt plus hydrogen. Al3 plus will be the cation. Cl minus will be the anion. 3 goes here, 1 comes here. So AlCl3. Okay. So metal plus acid gives salt and hydrogen. Now see, if I have now if I have some more reactions. This was the first reaction of a metal. The first reaction was with an acid. Second reaction. Reaction with water. So a metal reacts with water to form an oxide or a hydroxide and hydrogen gas.
Hydroxide.
So some metals may form oxides, some metals may form hydroxides. You have to know these examples which I have written. So the alkali metals form hydroxides. So sodium and potassium will react with water to form respective hydroxides, and also along with the hydroxides, hydrogen gas will be evolved. And the reaction is a vigorous reaction. Any alkali metal reacts in a vigorous manner. Remember this. It's a very fast and vigorous reaction. That means it is happening very nicely. While alkali metals are very reactive, and so they will react vigorously with water at room temperature. I mean, if you take cold water, then also it will react very nicely. So magnesium reacts with steam to form magnesium oxide and hydrogen gas. Zinc reacts with steam to form zinc oxide and hydrogen gas. So you have to know the conditions. I mean, you have to know where it is steam and where it is liquid water. So just remember these 6 examples. This is often asked that Fe. When iron reacts with steam, what happens? So you get Fe3O4, and Fe3O4 is called iron 2,3 oxide. Similarly, calcium plus water will give you calcium hydroxide and hydrogen. As I said, sodium, potassium, rubidium, these all react vigorously with cold water. What is Fe3O4? It's a combination of these two oxides of iron. FeO and Fe2O3. These two together form Fe3O4. Next, reactions with oxygen. A metal reacts with oxygen to form metal oxide. These are the examples. All reactions must be balanced. Again, you have to remember that sodium and potassium are extremely reactive, and so the reaction with oxygen is vigorous. Often they catch fire as a result of their reaction with oxygen. In order to avoid such a scenario, they are stored or immersed in kerosene in order to prevent the reaction with oxygen, which is present in the atmosphere. If you leave sodium or potassium just like that, exposed to the atmosphere, it will react with the oxygen of the atmosphere and it will catch fire. That is why we say that sodium or potassium should be kept under kerosene. Often they ask you in the exam, which are those metals which react on heating and do not react readily with oxygen? So you will say magnesium, aluminum, and zinc. Magnesium, aluminum, and zinc do not readily react with oxygen. They react on heating. Fe and Cu do not burn in air even on strong heating, but on prolonged heating they react. Prolonged means what? The process of heating is kept continuous. That means it is kept for a long time. It is ongoing. So after some time, then Fe will react. It's called prolonged heating, which means the heating is kept ongoing. Reactions with salt solutions. A more reactive metal displaces a less reactive metal from its salt solution. So you should know which is more reactive than the other. If a more reactive metal is placed in a salt solution of less reactive metal, then only the single displacement reaction occurs. Otherwise, reaction will not occur. Examples. In the first example, Fe is more reactive than copper. That is why Fe can displace copper from CuSO4 and form FeSO4 as one product. Similarly, zinc is more reactive than copper, and so zinc can displace copper from copper nitrate and form zinc nitrate as one of the products. Barium is again more reactive than zinc. So barium can displace zinc from zinc chloride.
So, what is the position of barium in reactivity series?
It is quite high. I have given you the reactivity series below, so you can have a look at it. Now, what happens is, in 10th standard, we usually don't show the position of barium, strontium, and all this stuff. But remember one thing, like a shortcut. You are supposed to remember in this manner that if I have any metal of group 2, so barium is a metal of group 2. As you go down the group, that means from beryllium till barium. As you go down the group from beryllium till barium, the reactivity increases. So in between what I have, in between
Sir,
I have,
can you repeat what you told in past few minutes? I was disconnected.
yeah, so I was saying that if you analyze the elements of one particular group, then the reactivity increases on going from top to bottom. That's like a shortcut which you can keep in mind. If I compare beryllium and barium, definitely barium is going to be much more reactive than beryllium. And also I can say that the order of reactivity will be like this: barium, strontium, calcium, and so on. So the most reactive will be this, and the least reactive will be this. Also,
Okay.
in a similar manner, I can carry out this analysis for elements of group 1. So what will happen? The logic remains the same. As you go down the group, the reactivity increases. So what should I write? Yes, what should I write? So I can write like this, metals. I'm going down the group. So last element is cesium, and here I have lithium. So reactivity wise, cesium will be more reactive, and lithium will be the least reactive. If I talk about the ease of reactivity, that is, which is reacting faster and which is reacting slow. So I can write this way. Correct? So this is going to be the most reactive metal inside group 1. That is cesium.